Have you ever wondered how scientists ensure the accuracy of their measurements? Welcome to our exploration into the world of significant figures. These seemingly simple digits play a monumental role in the realm of science. They are the key to maintaining precision and ensuring the validity of scientific data. Think of significant figures as the guardians of accuracy, the sentinels standing on the frontier of scientific measurements. They are not just digits. They are the markers of precision that keep our data truthful and reliable. They help us communicate exactly how certain we are of a measurement, so that our scientific integrity is never compromised. In essence, significant figures are the unsung heroes of scientific data. They make sure that our measurements are as precise as they need to be, and no more. Now that we understand what significant figures are, let's delve into the rules for counting them. So, how do you count significant figures? Well, let's get down to the rules. There are 4 main rules to keep in mind. First, all non-zero numbers are always significant. For instance, the number 5,432 has 4 significant figures: the 5, the 4, the 3, and the 2. The second rule is about zeros. Zeros between significant figures are also significant, so in the number 2005, the 0 between the 2 and the 5 is considered significant. This means that the number has 3 significant figures in total. Our third rule also involves zeros, but this time, it's about the ones at the end. If a number has a decimal point, then any zeros at the end of the number are significant, so in the number 20.0, the 0 after the decimal point is significant. This number has 3 significant figures. The fourth and final rule is a bit of a curveball. If a number does not have a decimal point, the zeros at the end of the number are not significant. So in the number 5,000, the 3 zeros at the end are not significant. This means that the number has only one significant figure, the 5. Remember, these rules are not arbitrary. They are designed to reflect the precision of measurements. The more significant figures a number has, the more precise the measurement it represents. Now let's run through a quick example putting all these rules into action. Consider the number 120.0. Applying our rules, we find that this number has 5 significant figures: the 1, the 2, the 0 between the 1 and the 2, the 0 after the 2, and the 0 after the decimal point. With these rules, you can now count significant figures. But how do we consider them when multiplying or dividing values? Multiplication and division can seem tricky with significant figures, but they don't have to be. Let's break it down. When you're multiplying or dividing numbers, the rule of thumb is that your answer should have the same number of significant figures as the number in your calculation with the fewest significant figures. It doesn't matter where these significant figures are located in your calculation, only their quantity matters. Let's illustrate this with an example. Suppose we multiply 3.14, which has 3 significant figures, by 2.2, which has 2 significant figures. The exact answer to this multiplication is 6.908, but since we can only have as many significant figures as the number with the least in our calculation, which in this case is 2, we have to round off our answer. So 6.908 rounded to 2 significant figures becomes 6.9. Similar rules apply to division. Let's say we divide 8.25 by 2.5. The exact answer to this division is 3.3. Both our numbers have 3 significant figures, so our answer can also have 3. Therefore, we don't need to round off in this case. But what if we divide 8.25 by 3? The exact answer is 2.75. However, 3 has only one significant figure, so we have to round off our answer to one significant figure. Thus, 2.75 becomes 3. Remember, the goal here is not to get the exact numerical answer, but to communicate the precision of your measurements. So, while it might feel strange to round off your answers, you're not making a mistake. You're just following the rules of significant figures, which are designed to ensure that your results are as meaningful and precise as they can be. That's multiplication and division sorted, but what about addition and subtraction? When it comes to addition and subtraction, decimal places come into play. You see, while multiplication and division with significant figures are all about the total count of significant figures, addition and subtraction are a slightly different ballgame. Here we are more concerned with the number of decimal places in our figures. Let's break it down with an example. Suppose we're adding 22.35, 22.35, and 4.1, 4.1. These numbers have 2 and 1 decimal places, respectively. When we add them up, we get 26.45, 26.45. But wait, we can't just leave it at that. We must consider the number with the least decimal places, in this case 4.1 with 1 decimal place. So our final answer should also have only 1 decimal place. That means we round our answer to 26.5, 26.5. And what about subtraction, you ask? It works in much the same way. Let's say we're subtracting 3.84, 3.84 from 20.01, 20.01. The result is 16.17, 16.17, but considering the number with the least decimal places, 20.01 with only 2, our final answer should also have 2 decimal places. So, we keep our answer as 16.17. It's important to note that sometimes the result of your calculation might have fewer decimal places than your least precise number. In such cases, you don't need to add extra zeros. The rule is to match the least precise number, not exceed it. By focusing on decimal places, we ensure that our results are as precise as the least precise number involved in our calculations. This keeps our answers consistent and reliable. Now, we can handle operations with significant figures. But what if we need to round off or truncate numbers? Sometimes we need to round off or truncate numbers to a specific decimal place. This is particularly true when dealing with significant figures. But what does it mean to round off or truncate a number? Let's start with rounding off. This is where we adjust the number to the nearest value based on the decimal place we're focusing on. For example, if we have the number 1.67 and we're asked to round it off to the nearest tenth, we look at the next smallest place value. Here, it's 7 in the hundredths place. Since 7 is greater than 5, we round up the number in the tenths place, giving us 1.7. Now, let's move to truncation. Truncating is somewhat simpler. We simply cut off the number at the desired decimal place without any rounding. So, if we're asked to truncate the number 1.67 to the nearest tenth, we ignore everything beyond the tenths place. This gives us 1.6. These methods of rounding off and truncating are especially useful when we want to maintain a certain level of accuracy in our calculations, but also keep our numbers manageable and easy to work with. Great, now we can round off and truncate numbers. But what about really big or really small numbers? Scientific notation simplifies writing really big or really small numbers. It's like a shorthand that keeps the number's value but reduces its size. Let's dive right in and see how it works. Let's start with a big number, say 1 billion. In standard form, that's a 1 followed by 9 zeros. Quite a mouthful, isn't it? But in scientific notation, we write it as 1 times 10 to the power of 9. The 10 to the power of 9 tells us how many places to move the decimal point. Now let's consider a small number like 1,000th. In standard form, it's 0.001. In scientific notation, though, we write it as 1 times 10 to the power of -3. The negative exponent tells us we're dealing with a number less than 1. So you see, scientific notation is all about making numbers more manageable. It's like packing a suitcase. You still have all your clothes, but they take up much less space. Scientific notation just packs big and small numbers into a more compact form. Remember, the number before the times 10 must be between 1 and 10, and the power tells us how many places to move the decimal point. Positive for big numbers, negative for small numbers. Scientific notation is a handy tool for dealing with extreme numbers. Now, let's wrap up what we've learned. We've covered a lot of ground today. Let's summarize. We started by defining significant figures, those crucial digits in a number that carry meaning contributing to its precision. We then moved on to the rules for counting these figures, an essential step in accurate calculations. We explored how significant figures are considered when multiplying and dividing values, and how decimal places come into play when we're adding or subtracting. We also delved into the techniques of rounding off and truncation, crucial when dealing with exactness in numbers. We didn't stop there, though. We also looked at how big and small numbers are written in scientific notation, making them easier to understand and work with. To tie it all together, we walked through the scientific method of carrying out an investigation, providing practical examples along the way. Remember, understanding significant figures can greatly improve your accuracy in science, and don't forget to search for WUNA Educational Services on all social media platforms.